Wow, it's hard to believe it's been only a year since we launched the App Bundle here at I/O. And what an incredible year it was. I'm Yafit Becher, a product manager with the Play London team.
And I'm Martin, a software engineer on Google Play in London. So today we're going to talk about what's new this year in the world of Android app bundles. So many developers have bought into our vision of optimized, tailored delivery and have already migrated to the app bundle. This includes some of the most popular apps on Play, seeing incredible size savings that range from around 10% to 60% versus delivering a universal APK. We really couldn't have hoped for a better acceptance of the app bundle among the developer community. And Google apps are migrating as well. So this includes apps such as Photos, Maps, and YouTube, which have dramatically reduced their app size, having switched to the bundle. So how is this achieved? Let's take a look back and remind ourselves what the app bundle is. So in essence, the app bundle is a new publishing format that replaces the traditional monolithic APK. But the app bundle is not installable directly. Instead, Play generates APKs optimized for specific devices from the single bundle upload. These APKs are much smaller than if the developer were to deploy a single APK for everyone, but the single upload provides a much simpler developer experience than uploading multiple APKs. So how does this work? So the smaller download size is achieved by delivering only the resources from the app that the specific devices need. Deploying a single APK would result in all languages, densities, and native architectures being delivered for all the devices. But as we see here, with the app bundle, only the relevant languages, densities, and native architectures are delivered, yielding a smaller install on the device and a faster download. So on average, the app bundle yields a 20% reduction in app size. This leads to faster downloads, which leads to an 11% increase in install successes, because there are fewer chances for the download to fail. And since less disk space is used, it also leads to a reduction in uninstalls. So since launch, more than 80,000 apps have moved over to the app bundle. Those apps are now publishing a single bundle and relying on Play to deliver smaller APKs to specific devices tailored for them.
But this is just the beginning. The introduction of the app bundle opens the door for new and exciting delivery features that simply wouldn't have been possible before. With the app bundle, we can build towards our vision of tailored delivery that optimizes all aspects of your app serving, from which part of your app to serve, to whom, and when. In order to take the app bundle to the next level, we are giving you greater control. And that's why our main topic today is Customizable Delivery, which puts you in control over how your app is being delivered. This will allow us to fully realize the potential of the app bundle, as it's you who knows your app and users best. Today, we'll cover 4 new product offerings that demonstrate the concept of customizable delivery. In-app updates that let you target updates directly from your app. Conditional delivery that lets you choose which feature modules to deliver to which devices. On-demand delivery that allows you to call for features only when you need them. And asset delivery for games that expands the app bundle to include game content, letting you package your game assets alongside your game binary and publish a single artifact to play. We'll also talk about internal app sharing that gives you an easy way to share test builds with your testers. Over to Martin to talk about in-app updates, our first product offering for today.
Thanks, Yafit. So auto updates are really great for seamlessly keeping your users up to date. But not all users receive them. Some are never on Wi-Fi. Others may simply have auto updates turned off. So some users end up using old versions of the app. Now, this isn't great for developers. For one thing, there may be a critical bug fix that you really need to get out to all your users. A new and strategic feature you're rolling out. A multiplayer game where you need to have all of your players on the same version of the app. Or perhaps you're simply looking to ditch support for very old versions of the app. Now, in-app updates, which we're launching today, gives you a way to trigger updates of your app directly from your app. It gives you control over the right contextual moment to start an update, while keeping the user in the app and not risking additional friction. So in-app updates come in two flavors: an immediate flow that triggers the update right away, requiring minimal integration. This is because Play handles the user experience during the update. And a flexible flow that lets you customize the user experience during the update. This requires more thinking and design work, but is ultimately much more customizable. So let's take a look at both of these flavors in action. So first, we'll take a look at the immediate in-app update flow with our sample Recipe Finder app. So as we can see here, the app triggers an update, and the user is kept in a managed flow until the update finishes. So first, the user confirms that they want to take the update, and the download size is revealed to the user. Then, the update is downloaded, during which Play manages the user experience, as we see here. Once the update is downloaded and ready for install, it is applied, and control is returned to the new, up-to-date, shiny version of the app. And the user can continue their journey inside the app. Now here, the developer doesn't need to do anything beyond the initial trigger of the update, which can happen when the developer chooses. Now, some developers will want more customizability than this. So here we have Swiggy. Swiggy is a food delivery app popular in India with more than 10 million downloads. Now, many of their users aren't regularly on Wi-Fi and so can't benefit from auto updates. But by using in-app updates, they can prompt the user to update while they're in the app and they have the user's attention. So as we see here, Swiggy have incorporated a small alert icon that notifies the user that the update is available. Then, when the user investigates, they're prompted with an opportunity to do an in-app update. Once again, Play seeks confirmation by displaying the download size. But for this flow, once the user has accepted, control is returned immediately back to the app. And the user can continue to use the app while the update is being downloaded. Finally, when the update is ready, Play will inform the app again, and the app can do something appropriate. For example, here, Swiggy raises a snack bar, which provides the opportunity for the user to complete the update by restarting the app, again into the new, shiny version of the app. So the flexible in-app update flow provides the developer the opportunity to customize the experience during the in-app update. So next, let's take a look how this looks like in code. So first, we acquire an instance of an app update manager from the Play core library. This is an object that lets you interact with the in-app update API. We make a call to find out whether an update is available. If it is, then we can act appropriately, perhaps triggering the in-app update flow immediately, or perhaps rendering some button that will do so once clicked. Now, the Java Play core API for in-app updates that we see here is available for any app to use today in Play core 1.5. But in the future, we'll be adding extension libraries for integration with Kotlin and Jetpack, leading to even simpler code. And if you're interested in seeing that, there was a live demo in the developer keynote. So that's in-app updates.
Thank you, Martin. Now let's talk about how to adjust the way your app is installed in the first place. Traditionally, all your code and app content are always served to all users. But sometimes you have features that are simply not applicable to some of the users or some of the devices. So by including them, your users get part of your app that they will never use. This is obviously not ideal. Conditional delivery lets you control which part of your app would be served to which users. With conditional delivery, you can set a set of conditions under which a feature module would be delivered and otherwise will be left out. This lets you exclude certain part of your app from some of the devices and avoid loading your app with irrelevant features to the device it's installed on, optimizing download side and on-device footprint of your app. We support 3 types of conditions for conditional delivery. First, you can have your module included only for specific countries. This is the first time Play has let you target part of your app this way. Second, you can restrict a module by minimum SDK version, targeting only devices above a certain version. And third, you can deliver your module only to devices that support a certain feature, such as a VR headset. Configuring conditional delivery is super easy. Once you've extracted the feature into a module, the only change needed is adding installation instructions to the Android manifest XML. The newly introduced install time elements allow you to specify conditions for delivery. You can include conditions for device feature, user country, and min SDK. We additionally support minimum OpenGL ES version. If you leave the install time element empty, the module would always be delivered. In this example, delivery is conditioned by device feature and min SDK. And the module will be served only to N+ devices that have an AR camera. The user country condition lets you exclude or include a module in specific countries, and you can specify more than one country. Here, the module will be deployed only to the United States and Britain. The device country in this context is typically determined by the user billing address attached to the Google Play account. As we've seen, conditions may be combined, and all conditions must be met for a module to be delivered. At runtime, you can call PlayCore API getInstalled module to find out which modules are installed. This can be used, for example, to guard access to a certain activity contained in the conditional module. Once the app is installed, conditional modules can also be requested to code, even if conditions weren't originally met. This is useful, for example, when you want a specific module to be served only to some of the users by default, while still letting other users get it upon request. Martin will talk next on how such features can be called for on demand.
Thanks. So that's modules that are conditional at install time. But sometimes at install time, you simply do not know whether a module is relevant for a user. Perhaps this depends on your individual knowledge of the user or their behavior inside the app after install. So what can you do then? On-demand feature modules can be used to install and remove modules during the lifetime of an app based on user behavior inside the app triggered via code. For example, this might be useful for user-driven uploads in a consumption app, which might only be used by a subset of the most engaged users. Other use cases might be an onboarding flow or a customer support flow that are rarely used more than once. So let's explore a case study, Netflix. So Netflix's customer support flow is a feature used only by a small subset of their users and is rarely used more than once by an individual user. But it is a fairly big component of the app at a few megabytes. So it's a perfect use case for a feature module delivered on demand. When the user clicks on the customer support option, the module is downloaded and installed. And once installed, it seamlessly opens, and the user can connect to customer support. This flow is live in Netflix today. Now, in future, Netflix will also configure installed modules in other ways. For example, it can remove the onboarding flow once the onboarding flow is completed. So how might that look? So let's take a look at the code here. So let's consider how removing a module would look in code like this. So first, the module is configured as an unconditional install time module. So this is a dynamic feature that's extracted and separate from the rest of the app, but it's installed for everyone when the app is installed. But by keeping it separate, when the time is right, it can be removed in code via the split install API in PlayCore. The Play Store will then mark the module for removal and remove it before too long, saving precious disk space. Now, on-demand and conditional modules are in general availability today and can be used in any app.
So we talked a lot about customizing delivery of feature modules. But the reality is that many times, the bulk of the content is actually coming from assets and not code. This is especially true for games, which sometimes require massive content download to even get the user start playing. We know that many of you are using CDN solutions to host and deliver your content from. But this results in a suboptimal user experience. User install and open the game, ready to start playing, just to be faced with the long progress bar, waiting for additional resources to be downloaded. Furthermore, since the CDN is blind to the device asking for the content, it can't optimize delivery to the requesting client. So you end up serving all assets to all users, regardless if they will ever use them. Another major downside of using a CDN is that you can't rely on auto-updates of assets. So again, this results in additional long wait for updating resources after the game is already installed. To make asset delivery seamless, we'll be releasing a new set of delivery options suited for games. With that, we are extending the app bundle format to include game assets, introducing a whole new delivery construct, the asset pack. Unlike feature modules, asset packs are composed of assets only, with no executable code, and can be very large. Asset packs will be packaged in the app bundle alongside your game binary, so you can publish a single artifact to play containing everything your game needs. You can also rely on Play to take care of keeping your assets up to date, just like it currently does with your game binary. And similarly to the flexibility you have with feature modules, you will be able to customize asset delivery according to your game needs. To start, you can use this to serve your assets upfront as part of the initial install, instead of using APK expansion files. Asset packs served this way won't require to publish an additional artifact to play, and unlike extension files, are not prone to accidental deletion by the user or other apps. Your assets can be easily accessed like any assets package in the base APK, using Android Assets Manager. You can sign up today for our early access program at this link, and will soon be able to include up to 1 GB of your game assets in the app bundle, avoiding the additional complexity of using APK expansion files. But again, this is just the first step. Stay tuned for further announcements later this year about additional delivery options, which will give you even greater flexibility and control, and allow larger asset packs and enable optimized device targeting, so that for game assets as well, your users will get only the assets suitable for their device. So let's recap the features we've discussed so far today. You can trigger updates directly from your app without having your users go to the store. You can condition the delivery of feature modules, and you can call for features on demand. And soon, you'll be able to package up to 1 GB of your game assets in the app bundle and serve it as part of the game installation. But a lot of what we touched on today relies on having your app broken up into modules. So to fully benefit from all this greatness, you should consider modularizing your app. Let's thank Martin and have Ben from our developer relation team get a little deeper on app modularization. We'll then talk about our last product announcement for today, internal app sharing.
Thanks, Yafit. Wow, that's a lot of new ways to ship your app to your users. But like Yafit just said, in order to make the most of it, your app has to be modularized. Traditionally, an app was served to a user's device as a single monolithic APK that contained all the code and resources and all the features to run all of your app. With the Android app bundle, that uses the split APK functionality introduced in Android Lollipop that makes use of this, so we can make use of all the features that we have seen today. Instead of packaging everything into one single monolithic APK, multiple configuration APKs are being built. Then, some of them, suiting the user's devices and preferences, will be installed on the user's device. This already saves your user precious data. You can achieve this by simply building your Android app as an app bundle and releasing it on the Play Store. So far, no changes to your code are required, but this already will lead to decreased installation size and faster downloads. But I'm here to talk about modularization. So let's take a look at what we did with an app that we made our sample app for modularized apps. We've gone through the process with Plaid. It's an app that we used to showcase a lot of features throughout the years. We used it for material design, to animations and transitions, and most recently dark mode. Also, throughout the past year, we made major changes to the app and modularized it, and added dependency injection using Dagger. The app consists of a home feed that displays gathered information. It also has a search functionality, an about screen, and several news sources that can be turned on and off. In the end, these user-facing features will be our feature module. But before we started modularizing, we switched over to app bundles. This allowed us to save a staggering 2/3 of the storage on some users' devices. We ship a native library, and by only having to ship the library for the CPU architecture that it's installed on, we save a lot of data already. From there, we were able to make changes to to the structure that Plaid has. Usually, your app consists of multiple things that tie in together, of code, resources, external dependencies, and drawables. After modularizing, the compiler will enforce clean boundaries between your feature modules through a directed dependency graph. So let's take a look how we did that within Plaid. No matter how you structure your code overall within the app, no matter which architecture you choose, you break that down into feature modules beforehand. Before we actually started making feature modules, we put everything into packages per feature. This allowed for a clean separation of concerns already. Doing that, we started untangling unwanted dependencies, and in the end, none of the feature modules should import code from another feature module directly. Then we went on and looked at our resources. We were particularly interested in structuring them in a way that we can move them to modules later on as well without problems. So for strings, we initially created files with a naming convention that reflects the feature association. We chose to add a module name as a prefix. That way, they still show up grouped together in the IDE. We then moved the strings into these feature resource files as we went along. We also renamed layouts, drawables, attributes in the same way, and then moved them along. This left us with shared sources, which we moved into a shared dependency called our core library. The core library is bundled once within the app space module and can be exposed to dynamic feature modules. This means the entire application is able to access these shared dependencies without unnecessarily adding to the app size. At this point, everything still was one monolithic module. But since we structured our app on a feature level, we were able to go on and create our real first dynamic feature module. We started using the most lightweight module with the least shared dependencies, our about screen. The Android Studio's new module dialog takes care of creating the basic setup. All we have to do is enter the module name and the package name. Directories are being created, and the correct dependencies are added in the app's Gradle file. Then we moved all the previously structured code and resources in the About feature into that newly created module. For most cases, it was a fairly lightweight process, but some did take a little bit more work and thinking about. So let's talk about these. As we are using resources from both the About feature as well as from the core library, imports came from different R files. They became a bit tedious to read. In a monolithic application, you usually have one single of these files, so that's not a problem. But if you import for multiple packages, you can end up with imports like this. We're able to resolve this with Kotlin's import aliasing. It's a feature that allows you to map an import to another name. So instead of having to write a fully qualified import for app's R class, we simply remapped it to app R. This led to more concise and readable code. Differentiation is still possible and easy, but it's way less noisy to read. Another thing we had to change was the way activities are launched within the app. In a monolithic app, it's possible to pass the class directly to the intent explicitly. Even activities within a library dependency can be explicitly launched. The dependency is directly accessible from within the app space module. But a dynamic feature module depends on the app, which makes its content invisible to the app module. This means that classes in a dynamic feature module are inaccessible to the app module. So instead of passing the class directly, we now pass the fully qualified class name. The Android framework is able to instantiate and start the activity as it usually did. An app containing fragments in a dynamic feature module can use reflection for instantiation. A key to modularizing is also having a single point of responsibility for actions the app can take. So we didn't want to maintain these weakly typed calls throughout the entirety of Plaid. So we introduced the addressable activity interface in the app's core library. Then we implemented it for each of Plaid's activities. When needed, these objects can also hold keys to intent extras in a single place. This allows for centralized code that can be invoked from any module. Alongside with the intent to function, this makes launching the activity straightforward and type safe. This allows for decoupled code that can be invoked from any module, as well as easy to read. Even before making use of on-demand delivery, we have reaped various benefits. Plaid's build time dropped from 3 minutes down to 1 minute for a clean build. This was achieved by using Gradle's parallel build feature, which enables us to build multiple independent features at once. Up to a certain limit, separating out more independent features will further decrease the build time. Overall, we gained a more maintainable app. This is due to self-contained modules and compile time enforcement of separation. Also, our app's footprint has dramatically decreased. This results in faster app downloads and saves precious storage on device. So, looking back at our tracks that we took so far, we first identified the features of the app that we wanted to modularize. In our case, those were the user-facing features that the app already had. Then we started moving the code and resources to match the structure. Afterwards, we created a feature module and populated that. Our modularized architecture will allow us in the future to dynamically install modules as we need them. This works by depending on the Play core library and making use of its functionality. We can request dynamic feature modules as they are needed and start installing them. Also, if users disable features for a longer time, we can easily uninstall them if they're no longer needed. For more details on how to do that, check out the sample app as well as the Play core library documentation. You can follow Plaid's development on GitHub. Also check out an article containing more in-depth information on the modularization process. Thank you very much. With that, back to you, Yafit.
Thank you. Now let's talk about testing a bit. Since we launched the app bundle, we kept hearing from developers how great it is. But there's one thing we heard from you loud and clear. Testing of the app bundle is hard. This is especially true early in the development lifecycle, where you simply want to share a test build with your internal testers. In the APK world, it used to be very easy to do. You simply send the APK, and the platform knows what to do with it. But app bundles are not installable. And with Play, tailoring the served app to each device, you want a guaranteed way to get exactly the same binary as your users would get. You've asked, and we've heard you. Internal app sharing, launched today, gives you a quick and easy way to internally share app bundles for testing. All you need to do is upload a bundle to Play, get a shareable URL, and have your testers use that URL to download and test the app. This is how it looks. You simply drag and drop to upload and share the generated link with your testers. With internal app sharing, the app installed is exactly the same as if it would have officially published to Play. It even supports dynamic delivery features, including on-demand and conditional delivery. This way, you have full confidence that what you are testing is the real thing, and you can expect exactly the same behavior as your users out in the wild. You're probably curious to hear more about how it works. So let's have Serge, who led the development of internal app sharing, dive into the details a bit.
Thanks, Yafit. Hello. First, I'd like to clarify that internal app sharing is fundamentally different than our existing testing programs. Simply put, it's not a release track. With internal app sharing, the test version uploaded to Play are served and hosted by Play independently. They're not part of a release published in the Play console. So let's touch on a few important features. First, each test version, uploaders don't need to be Play console members. So you can authorize users that don't have access to the Play Store. Test versions are re-signed by Play with a test certificate, so uploaders don't need access to the production or upload key of your app. Play doesn't require unique version codes, so multiple uploaders can use this feature independently, and they don't have to pick unique version codes when they upload. Debuggable artifacts can also be uploaded, so you can debug the APKs once installed on the tester's devices. To authorize testers, you can go to the Play console and choose to either allow anyone with the link to download and install APKs, or to allow only users in predefined lists. In both cases, there's a user cap enforced by Play. So let me show you how it works in practice. Can we switch to the laptop, please? Can we see the lap? Yes, excellent. So I have an app bundle here on my desktop. I just did a fix for a bug that was reported, and I want to quickly share it with my QA engineer for validation. Obviously, because it's an app bundle, my tester cannot simply install it on the device. So what I will do is that I will load the new internal app sharing upload page, and I will drag and drop the bundle onto that page. Again, here I don't have to worry about version codes, because I'm guaranteed they won't conflict with the artifact published in release tracks. It shows a dialog, and it shows the version name of my app bundle that is extracted from the Android manifest file. I can choose to change the version name, so my tester knows what this test version is about. Here again, my uploader account doesn't need to have access to the Play console. It just needs to be authorized by the Play console admin for that app. Now that the upload has completed, it shows a shareable link. So I can copy that link, and I can send it to my tester. Can we switch to the device, please? Amazing. So I have my tester's device here, and within a few seconds, I should get the email. So my tester opens the link and installs the app. So there it is. Super simple and quick. This is a version of Gmail that I built, and I changed it so that there's a dynamic feature module for the compose activity. When I tap on the plus button here, it loads a feature module, and it's installed by Play. It works right away because the app is installed by Play. But even better, because my bundle is debuggable, I can take my device, and I can connect it to Android Studio. I can attach the debugger to that process, and I can step through the dynamic delivery code. So that's super useful. Can we switch to the both devices, please? All right. Let me do that again. I can step and through the dynamic delivery code. More than that, we also build an API endpoint and a Play Publisher API so that you can automate publishing artifact to internal app sharing. And you can integrate it with third-party tools. So you can even, for instance, invoke it directly from Android Studio. So this is Play, internal app sharing. Thank you very much.
Thank you, Serge. So just in case you've missed it, using internal app sharing, Serge was able to locally debug dynamic delivery of an on-demand feature. Isn't that cool? We hope that this presentation demonstrated our commitment to the app bundle and that we are doubling down on our vision of customized dynamic delivery. In-app updates, conditional delivery, dynamic delivery, and internal sharing are all live with documentation available at developerandroid.com. If you are interested in trying out upfront asset delivery, join our early program at the link. We'll have more to share later this year, so come and see us at events like the Android Developer Summit and Google Playtime. Thank you.